Hello AP Calc students, welcome back to our second and final video over topic 10.7, all about the alternating series and determining convergence and divergence. Now, in this video, you have to keep in mind that we have yet to discuss the difference between absolute versus conditional convergence, which is coming up in a couple of more topics. So this is just the basic introduction to alternating series behavior, and then we will polish that up when we get to topic 10.9. If you recall from the last video, we outlined what we call Theorem 10.7, our alternating series test, and basically said you've got an alternating series, which means you're going to have this alternating component that might look like -1 to the n or -1 to the either n plus 1 or n minus 1 power. And that's going to be hanging out with some nth term expression here that I've highlighted in orange. There are two different criterias that have to be met. The first one is if the limit of that nth term expression as n approaches infinity is 0, and notice both of these have to be met. If the nth plus 1 term is less than or equal to the nth term for all n, then we know that we have ourselves a convergent alternating series. Now, we're going to talk a little bit about this second criteria because sometimes it can be a little tricky. Let's take a look here at this next page, and I'm actually going to have you just take a quick look at the example first. We're going to show that this alternating series converges. Well, that alternating series has got quite a mess going on with it, especially with that denominator and that factorial. And a lot of times when you have things that are a little bit more complicated like that in your alternating series, verifying that criterion number 2 can be a little bit more challenging. So here in the green box, I've got a couple of ways, really 3 ways by which you can embark on that particular journey. The first way is called the algebraic difference. And it's just saying, show that your an minus 1 minus your a sub n is less than or equal to 0. Well, another way to say that is show that your an plus 1 is less than or equal to a sub n if you add the a sub n over, which is exactly the way that I showed in problem example 1 part A, if you recall. If you feel like that's going to be challenging, and I believe for example 2, that might be a little bit tougher. If that's a problem, you could think about using the algebraic ratio instead. And that way, that procedure just says to take the nth plus 1 term and divide it by the nth term. And if that ratio is smaller than or equal to 1, that means that your series is going to be non-increasing, right? You have a ratio that's a fractional value potentially less than 1, and that kind of indicates that those terms are gradually getting smaller. All right, the third criteria, maybe not our most desired way, but you could equate some continuous function f of n with your a sub n, and then you could even kind of relate f of x with f of n, and you could use the first derivative test. Now, if you recall, we had to do that quite a bit when we were working with the integral test and its third criteria. So I would say use the test that you feel most comfortable with. Just try not to get lost in that part of the problem because you have more, there's bigger fish to fry is the phrase that comes to mind. So we want to make sure that we can get through this fairly quickly so that we can move on to the actual real conclusion. All right, I have the theorem here off to the side so that we don't have to scroll back and forth. So we should be able to move on to this. And one of the things that I wanted to mention here in this problem is one of the criteria is that your nth term expression, and that's the piece without the alternating component. Remember, we do have to have a positive nth term expression. And so I believe that 1 divided by 2n quantity factorial is indeed positive for n greater than or equal to 1 in this case. Okay, so we then go to criteria 1, and that would be to say, what is the limit as n approaches infinity of 1 over quantity 2n factorial? Well, a lot of times we have the statement that calculus and factorials do not get along sometimes. They just don't seem to play nicely with one another. And so if we think about, well, what's going on with this particular limit? Well, it's very likely that you're going to see that this bottom is going to get huge in a hurry. Whether the factorial is there or not, it's going to get huge in a hurry. That factorial being there is going to make it get huge in a big hurry. And so it's very clear that this is going to be 1 over something super large or ultimately 0. Now we can move on to the second criteria. And this is the one that I wanted to kind of think about a little bit here. As I said before, I think the algebraic difference might be a little bit trickier. And so I'd like to investigate the algebraic ratio. In other words, I want to basically analyze, is this statement right here, question mark, a true statement? Well, we can investigate this by taking that n and changing it to an n plus 1. Now, all of this would still have to be wrapped in parentheses and applied the factorial. And then the bottom is just going to be 1 over our 2n factorial. So we're still questioning whether or not this statement is less than or equal to 1. All right, I'm going to actually come up and work in this space. Let's go ahead and multiply by our reciprocal, which is going to give us quantity 2n factorial over quantity. And I say that we go ahead and distribute our 2. So we would have a 2n plus 2 here with our factorial. And we're still questioning, is this less than or equal to 1? Well, now we're going to have to figure out, how are we going to simplify this thing? And so the thing that I want students to always remember is that factorials written in ratios like this are very conducive to canceling a lot of terms. By that, I mean this denominator 2n plus 2 is actually going to be the same thing as the term 2n plus 2 multiplied by the next integer below him, which is 2n plus 1, multiplied by the next integer below him, which would be 2n, and I could continue to do that, 2n minus 1, 2n minus 2, etc. But in lieu of writing all of those extra expressions, 2n minus 1, 2n minus 2, etc., isn't that the same as just the factorial there? And then I'm still making the conjecture, is that less than or equal to 1? Well, now you can see this wonderful cancellation that's going to occur there. And it brings me to the statement 1 over the quantity 2n plus 2 times 2n plus 1 is less than or equal to 1. And I feel very confident that that has got to be a true statement. Because remember, n has got to start with 1. Therefore, this seems only logical that that's going to be true. Because if you let n equal 1, already you're going to have, well, what would this be if n is equal to 1? 1 over 4 times 3, right? So you'd have 1/12. And that's certainly less than 1. And as n gets bigger and bigger, this is going to become even smaller and smaller. So I think we can check and check. And because of those two statements being true, we know that that means that the original series, the summation as n goes from 1 to infinity, of -1 to the nth power over 2n quantity factorial is going to converge. Now, what's going to become even more interesting down the line is to determine how well this converges, because it could converge conditionally or it can converge absolutely. And that's really the question that you would have to be able to address on the AP exam. And we're going to take a look at that here in just a couple of more topics. Anyway, I hope this helps out. This wraps up our 10.7. We look forward to seeing you at 10.8, the final test, the ratio test coming up then. Thanks for joining. We'll see you next time.